In this video we discover basis vectors and a way to represent vectors in a more general fashion. Basis vectors allow for uniform representation and transformation of vectors without mixing spaces. Hi, my name is Alex and this is another video in the series about math for coding with vectors. Let us begin with two vectors which are orthogonal to each other. Those two vectors represent the usual space we know so far. It allows us to travel in x and y direction. Each of those vectors represent one direction denoted in the subscript of the vector's name. So ex travels in x while ey travels in y direction. The most basic form is the 1, 0 and 0, 1 basis. Additionally, we define some rules we need to ensure every time we work with basis vectors. The first being ex and ey need to be of unit length. The second is that ex and ey need to be orthogonal to each other. Because of those two rules, the pair of vectors form an orthonormal basis, and it is very simple to apply those rules since we always construct the basis ourselves. Using this basis, or frame, we can write a vector v in terms of an operation. That is, multiplying the components of v with the respective basis vectors and adding those together. This operation is called a linear combination. In our example so far, after adding those scaled basis vectors, we end up with the same vector v. Note that in our example here, the basis does not change, so the result is still v. Now let us change the frame so we can see the real advantage of this representation. In a previous video we went through orthogonalization. Let's revisit the frame we discovered and developed there. This is the very genius cosine sine frame. As a short reminder, this frame rotates the ex vector and keeps ey always orthogonal by applying the 90 degrees rule. We do not need to normalize the vectors because this basis always comes normalized already. So let's put it in the equation and see what happens. Substituting ex and ey with the new basis, we can see the effect this new basis has on vector v. It takes vector v and transforms it into vector w. In a sense, this transformation applies a rotation to the input vector v by performing a linear combination. But there are actually two ways we can see this operation. One would be that this operation rotates the vector itself. The other would be that this operation transforms the frame while the vector does not change. The important takeaway here would be that this transformation is not tied to a specific vector. You could take any vector and apply the transformation. If you wanted to combine another vector w with v, w needed to be transformed into the same space as v or vice versa. That is, transforming any w into the space before the transformation is called the inverse transformation, and it is denoted by a -1 in the superscript. So in our example, ex and ey would rotate a vector counterclockwise. The inverse operation would be a clockwise rotation. So naturally, we simply put the same angle but negate it into the trigonometric functions of our basis in order to rotate in the opposite direction. Once again, looking up all the trigonometric identities, we will find that cosine of -phi is the same as the cosine of phi, but sine of -phi will change to minus sine of phi, so the basis vectors change a bit. Please look carefully, the sine functions change place. We will cover this fact in the next video about matrix operations. To summarize, the basis vectors allow for a forward transformation from local space into the reference space. On the other hand, the backward or inverse transformation changes any vector from reference space to local space. In advance to the next video, let's dissect the operation. Here we only view the transformation itself. First we have a transformation M which represents the identity I, that is doing nothing to the vector. The frame is unchanged. The second transformation M is a rotation which we name R for now. As you can see, R operates on I, which we can interpret as taking the local frame to the rotated frame. And lastly, not covered so far, we could use any constructed basis A as a transformation to represent a vector in. For any of those basis vectors, if kept orthonormal, we will discover a very simple way to construct an inverse in the next video. Let's look at the same scenario with vectors now. We write the transformation of any vector v to the right of the transformation. The transformation is applied from the left. First, I does not perform any transformation to v. Second, V is kept in a local frame which is transformed by upper R. Third, V is transformed by any basis upper A. Each of those transformations we can compose any combination of transformations to form a single transformation upper M and apply it to V. Finally, to summarize the video, we apply a forward transformation in order to transform any V from a local space to a W in reference space. Likewise, in order to take any W in reference space back to a V in local space, we can apply an inverse or backward transformation. In another video, we will combine the concepts of a forward and backward transformation to achieve visual motion in computer graphics, called affine transformation. In this video, we covered basis vectors, which help transforming vectors from a local space to a reference space. We will dive deeper into this topic in the next video about the matrix. I hope this video will help you digging further into this topic. Until next time, stay safe, like and comment. Bye now.